So welcome back. This is the time where we really start our introductory course in quantum mechanics. And so let's set the stage for whatever will happen in the next several lectures. So what we concluded last lecture with was the concepts of border between quantum realm and classical realm. Remember, we have split, we consider a plane where we pictorially represented the space or length scales on the y-axis and time scales on the x-axis. And on this plane, we have put different biologically relevant entities, including, animals, cells, all the down to microscopic objects such as atoms. And so where is macromolecules? And we, came up with this sort of idea that the physical theories that were developed in the late 17th century, early 18th century by Newton and Galileo, and then later on all the other scientists that contributed to that form what today is called classical physics, or in particular classical mechanics, do not work as you approach the lower bottom corner of this plate. And in particular, we came up with the idea of this fuzzy border that splits the physical objects that change their state and they evolve in time according to the laws of classical physics, and the physical objects that do not follow those rules and follow the rules of quantum mechanics. We call this the quantum realm and the classical realm. And macromolecules sit in the middle, according to the ideas that we discussed in the last lecture. So we also concluded with the idea that if you want to understand nature, biological matter in the reductionist approach, i.e. in a Russian doll bottom-up manner, starting from most microscopic elementary entities and then building up layers of complexity in a systematic way, you must route your path into quantum realms, starting from atoms, and then move in these directions and understand from atoms molecules, and from molecules maybe collections of molecules all the way to cells and then to organisms. So that's the reductionist path. Let me call it here. Reductionist path. And therefore, this is the reason, and that was the main point of last lecture, why we need to study quantum mechanics to set the beginning of this line and use it as a starting point to develop everything that follows. Okay? Sounds very good. So, how do we start a course in quantum mechanics? In the last course, last lecture, we rapidly glanced over the fact that quantum mechanics is mathematically and conceptually very different from classical mechanics. So there's one of the largest leap in science involved in the transition between classical and quantum realm. So my personal way of approaching this will be based on revisiting classical mechanics for a couple of reasons. So the urge for revisiting classical mechanics comes from a number of needs. First of all, because we want to understand So goal number one, understand where it fails. So, the idea is to approach quantum mechanics somehow in an historical way, the way that it was discovered 1 century ago, which is basically looking at the quantum realm this way. People were going more and more microscopic as technology was growing more sophisticated. And then when they reached the quantum realm, the borderline between the quantum and classical realm, they realized it because predictions they were making in classical mechanics were not longer verified by the experiments. And the experiment was beginning to show very unexpected behavior. And then led to understand that even concepts such as an atom was not even possible in classical mechanics. So one reason for revisiting classical mechanics as a starting point in quantum mechanics is to understand better the failures of it. So you study it to understand its failure. And the second, perhaps less clear from the point of view, less clear at this level, reason for revisiting quantum mechanics, now goal number two, is to clarify / define, depending on where we have it already sort of clear, or we have really to start from scratch, the notion of physical theory. Okay, so this is of course less clear than the previous goal. What it means to clarify and define a notion of physical theory. It is a collection of words that I expect to make no sense to you at this level. So all I'm asking you at the moment is to write it there, and maybe at the end of this lecture, I will begin to glance at where I'm aiming to when I say we need to define the notion of physical theory. But from a practical and pragmatic perspective, you can think about this goal number two as preparatory work to change our mind and make it ready to accept a completely different formulations of physics, which is the quantum mechanics. Because you see, the typical problem that many students encounter, including myself when I was a student, in going along the reverse reductionist path, which is the path that led to the discovery of the quantum path, this path, is that the mathematical formalism of classical mechanics, the setting of classical mechanics that you learn in college or in high school, and you think you understand, is completely different from the language in which quantum mechanics is formulated. The mathematical object seems very different. The main actors look very different. You have Newton's law on the one hand, where you have positions, velocity, and forces, and then all of a sudden you have operators, wave functions, observables, and things become very weird, and you get lost. You don't understand whether you have to develop two independent brains, one for classical mechanics and one for quantum mechanics, because the two lobes of our brain seems to be very difficult to connect, because quantum mechanics and classical mechanics at the superficial glance look very different from one another. However, if you do this effort of revisit for a moment what is in fact a physical theory, then in a more broader perspective, what it means to be doing a physical theory, then you realize that from this more general viewpoint, quantum mechanics and classical mechanics don't look so different anymore. Actually, they look very similar to a point that it's relatively easy to make a transition. So you should think about this as, you know, suppose you are on you know, you're an ant working down a park, and you're looking at the world from the ground, and you see there are, I don't know, bushes and flowers and a little pond, and they look very different from one another. But then, right, somebody takes this ant, lifts it up, and all of a sudden the ant looks at the same thing from a broader perspective and discovers that this is all part of a pond with similar rules, and there's another world and another world called the street, and you know, and all of a sudden things that look very distant from one another, the concept of flower and the concept of I don't know, leaf, become similar. You start developing analogies between the two, and sort of a enlarged understanding of the world. So remember, one of the challenges of quantum mechanics is to twist your mind. So we will do that likely at the next lecture. And we will need some tools in order to do that, which we'll develop in this lecture. The third goal of revisiting classical mechanics is to make sure, so let me go, okay, this goal number 2, I erase to make space. And then I'm going to goal number 2, is to refresh on, so goal 3. Goal 3, refresh on some key concepts. So in classical mechanics, there are concepts. I'm just realizing the screen has been frozen. This happens sometimes, and the only way I can do this is by stop sharing and resharing. And to do that, I have to here mirror again, and now it should work. Okay, so I was saying refresh some of the key concepts. And you know, these are concepts that you should be familiar with, such as conservation laws, mechanical energy, work, and potential energy, kinetic energy, that are transferred from classical mechanics to quantum mechanics. And I want to make sure everybody's on the same pace for that, on that, even though the backgrounds might be different. So here are the 3 goals while we will go towards revisiting classical mechanics as a first step in developing a theory for quantum realm. Okay, so classical mechanics is a collection of physical laws. Classical physics, I would say, is a collection of physical laws. And if I were to ask you what is classical mechanics, you probably would say is the result of applying Newton's law. And I would not list Newton's law. I will only list the most practically important law, which is the one that connects the acceleration of a particle to its force, to the force of acting on the particle. I'm writing this for a single particle. If you have more particles, then you have more accelerations, and things get more involved, but we'll go to that later. So this is the particle acting on my particle, and let's stick to the single particle for now. In the next lecture, we will see that already in this course, in this equation that everyone should be familiar with, there are very hidden subtleties, and this equation is by no means a simple equation. It's no means self-explanatory. What this equation really means is probably less trivial than you would have thought, but wait the next lecture to dig into that. At the moment, let's be very pragmatic and say you know, this equation, of course, means nothing until I specify what a force for this system is, right? And for instance, this can be gravitational, electromagnetic, and these are examples of fundamental forces, meaning forces that are present even at the most microscopic level between particles. But there are also emergent forces such as, I don't know, friction. Friction is not a fundamental force, it's just the effect of having many particles colliding together. It's a collective phenomenon that only, you know, concerns microscopic particles and stuff. So if you have a way to providing this equation with the right-hand side, then this equation is actually an equation that connects the second derivative of my position, of my particle, to the ratio between the force that is acting on my particle at a given time, possibly as depending on the particle position, the velocity maybe, and who knows, other things such as, I don't know, an external force. Maybe you have a particle in an electric field that somebody else is explicitly changing the strength of the magnetic field. So even if you're in the same position, the force that you keep changes with time because somebody else is putting a larger battery in your system. So there could be explicit dependence on time as well. Fine, these are all details. The main fact is that once you have this equation, if you can solve this second order differential equation, then you can get the low motion, meaning you can get the position of a particle at any time t in the future. So here already is the main goal of mechanics, you know. Tell me what is the particle's position and velocity at some time, and I'll tell you where the particle will be in the future. And there is probably, it's not by chance that the development of mechanics happened right after a technological innovation that struck Europe in the late 17th century. That is, the fact that gunpowder became very popular. You know, people started to develop guns and cannons. And rather than having to be aiming all the time with the subject of human errors based on intuition, it is possible that all this was developed by the need of being able to predict the cannonball trajectories. Just to say one, you know, unfortunately, you know, well, I'm bringing this up because sometimes, along with epistemological frameworks such as, Popper and Kuhn's epistemological theories for how physical theory developed in context with their social environment, there might also be much more down-to-earth reasons related to economic or even war-related matter. Think about how much physics was developed during the Manhattan Project, right? So, but all this is to be saying that the particle is supposed to be projected, and you want to know exactly where it will land, for instance, right? This is one of the typical goals of classical mechanics. Okay, so this is how you formulate classical mechanics, and typically it's all there is. What I'm trying to say is that once this equation comes from nowhere, meaning there is no mathematical derivation of this equation unless you know quantum mechanics, from which you can derive this equation as a consequence in the large world. But a physical law follows from experiment the first time you derive it. There's no reason it is that. You cannot demonstrate it like a theorem. It is something that, you know, you have tried, put in your hands on nature, and eventually came up with a number of observations that could be well rationalized by this force. So don't try to understand why you have accelerations and force. Just know you have acceleration and force related to this relationship and use it to predict. That's how physics works. The law comes from experiment, the implication on the law for the predictions and the future, and whatever they need for you, that's on the researchers. So, okay. So once you have Newton's law, basically you have all the classical behavioral particles. So, okay, along with these concepts, along with classical mechanics, second Newton's law, you are often exposed in your high school education or college education to additional concepts, which are work, energy, let it be kinetic or potential, angular momentum, linear momentum, and so on. All these concepts are not fundamental in defining classical mechanics, a la Newton. In principle, you can get all the predictions from classical mechanics directly by solving Newton's equation if you're strong enough, for instance, by using a computer. But of course, these concepts that are listed here are extremely useful if you want to solve problems that are complicated without using a computer, for instance. And if you want to gain insight into the implication of classical mechanics without having to solve classical mechanics. For instance, you know, the famous example is, you know, I know that if I have a big pendulum and I want to throw a pendulum, the pendulum will not swing over to a higher point to respect to where I throw it if I throw it with zero velocity, because if by the time it gets here, it will have the same energy, it will the same potential energy that at the beginning, and since there's no kinetic energy, then the energy is conserved, and you would violate the conservation of energy. These are concepts that you heard sometimes in the past. Let me draw it just to make you understand. So you don't need to solve Newton's equation to know that if you have a pendulum and if you drop it from this position with zero velocity, it will swing to an equally high position on the other side and then swing back here. Or lower because of friction. Because this is just a consequence of the powerful concept of conservation of energy. There are other consequences that involve angular momentum and linear momentum, and we will go through that later on in this lecture. But all I want to emphasize here is that none of these concepts is really defined in classical mechanics. We shall see later that when we want to perform a transition to quantum mechanics, we will formulate things in a different way, and we'll reformulate Newton's law in a more rigorous form, if you want, in which this concept will come in from the very beginning somehow. And so the hierarchical order in the degree of being fundamental for a theory of this concept will be reshuffled. But that's for the future, not for right now. So what I'm going to do in this lecture is just review these concepts and then just discuss a little bit what they mean. Okay, so let's start. Let's start with the concept of work. A bit of boring freshman physics here. But if you haven't seen this for a long time, maybe it's not so bad that you get over it. Okay. So suppose you have a particle that is moving along a certain trajectory. That's the path of that particle. And let's suppose that this particle is subject to some force F. Well, the work of the force F exerted while the particle was going from A to B along this path is a function of the path, of course, and is defined as follows. Now, this is a complicated expression, and I'm going to tell you what it means in a moment. So A and B are two positions here, so they are vectors. And what is this meaning? It means that in order to compute this mysterious concept called work, all I have to do is to split this path in many little pieces. How short should these pieces be? Well, they should be short enough so that the force is not changing within each of these little intervals. For instance, you see, if I look at the force here and I look at the force in this point, they are not the same force. So the force has in fact been changed over this large distance. But if I were to compute the force here, maybe the force here would be just almost constant within this distance. So that's how many pieces I should divide. So let be this, each of these be of size delta x. And so what do I do to compute the work? I take in each of these pieces, I look how much distance I have made, delta x. I'm using delta to remind myself these are in principle finite pieces. And I compute the inner product or scalar product between this displacement delta x and the force calculated in the beginning of this interval, in particular here. So let xi be the displacement starting from the ith little bit of segmenting the trajectory. This is my ith plus 1, ith plus 2, and so on and so forth. And basically, I have to compute all of this product between the displacement and the force. Now, if you don't remember what is the inner product, I encourage you to go on your refreshment book and refresh it. And we cover that from a formal perspective also in the mathematical background sessions of these courses. And after you're done computing all of this little inner product, what you need to do is to sum over all of that. So there are n of them. Now, if you have chosen this little sizes, little displacement to be short enough so that the force would be almost constant within each of these small segments, you will realize something interesting is going to happen. You know, when you begin and you choose a delta x that is very large, say you use this as delta x, you're discretizing the path in large leaps. The force is really not constant over these intervals. So when you start doing something more precise and you use 2 steps, you're going to get a different result in your estimate of this sum. However, at some point, when the force begins to be constant within delta x, whether you choose delta x or half of it and sum twice as many per terms, will lead essentially to the same result because you are converging to the right amount. You're converging, your estimate is becoming more and more accurate, and basically it doesn't change anymore. Maybe, this is your estimate of the work. This is the size of your interval you use to discretize the line from A to B. Now, as you start here with a large size, and you start maybe half of it, and you get a different result because the force was not constant with it. Then you half of it get a different result, but at some point it doesn't change anymore. because you're really reached an agreed, or you're very accurate, or whether you make it even more accurate, it doesn't really matter. So in this regime, your sum is accurate. And when this sum becomes accurate, you call this a line integral between dx cross f of x from a to b. And if you want, you can call this a definition. Integral is, the line integral is really the limit in which you've chosen sufficiently, you've discretized your path in so many pieces that eventually you're so accurate that if you take more pieces than you've used, nothing is really going to change anymore. Okay, so why do we need the concept of work? Why do we want to use the concept of work? Well, because work enables me to get some information about the physical system without having to solve Newton's law. And remember, Newton's law is a damn difficult equation to be solving because it's a second-order differential equation. In order to know the position of the particle, you have to find a function whose double derivative, second derivative, is in fact equal to the force calculated in that realistic space. If there's velocity, you also have to include other information here, but let's suppose simply the force depends on the position. And this is a very complicated function, complicated problem to solve. Even simple problem involve heavy math. But if you introduce the concept of work, you get some information almost for free. And what kind of information you get for free? Well, to see that, we introduce a second concept, that is concept of kinetic energy. Kinetic energy is simply, I call it T, some people call it EK. Let's call it T. For a single particle is 1/2 the mass of the particle times the velocity of the particle squared. For multiple particles is the sum of this quantity for all the particles in the system. So for many particles, this would be sum over I, 1/2 and I squared. And why do I care about kinetic energy? Because kinetic energy and work are actually related by a very useful relationship. How do I know? Well, let's take the time derivative of the kinetic energy. Well, you can do it the following way. Assuming that mass doesn't change with time, which is true in classical mechanics, whenever the particles don't move at any speed close to the speed of light, when the particle becomes very fast and move near the speed of light, then you have to use different laws. There are laws of Einstein's relativity. We are not concerned about that because none of the particles that are involved in biological molecules move at those super high speed. So let's imagine the mass is constant. Whenever you apply the derivative, we can go through the derivative, and then you have the derivative of the velocity against the velocity. And now you should remember some laws of differentiation, which I don't, of course, have time to review here. So when you have the derivative of a product of variables, you should, a function should differentiate. First, the first keeping the second not differentiated, and then the second keeping the first not differentiated. So one famous rule of differentiation is that this guy is like dv by dt cross v plus v dv by dt. Right? Now, we realize This guy is these two guys are, well, first of all, I can collect them because, the inner product is symmetric with respect to changes of the order of the terms being multiplicated. So I can say, let's forget about the second term here and put a 2 here, which will cancel this. Okay, so what we discover is that the derivative in time of the kinetic energy is actually the mass times the velocity times force. Why the force? The force divided by the mass. Because the velocity divided by the time derivative of the velocity is actually the acceleration. And the acceleration by Newton's law is the force divided by the mass. So you get this. So what did we get to? Now I'm gonna be very sloppy on the math. The point of this course is not to be rigorous. So if you're a mathematician, you'll probably be horrified by the way I manipulate these mathematical objects. That's fine. It's better to be a little bit sloppy with math than to have all the people who have idiosyncrasy with respect to math be chased off by this lecture. So what I do, I consider this as a variation of kinetic energy with respect to a variation in time. And I do this as a variation in position with respect to a variation in time. Times f divided by m. I can take off this. Now, if I'm interested in summing and considering what is the change of kinetic energy when the particle was going from A to B, I want to split this into little pieces of size delta x, and in each of these pieces, for each of these little segments, the particle took a time delta t to go from here to here to here to here to here to here. Now, from this equation, for each of these small segment, the kinetic energy changed by this factor. So if I want to find out how much the kinetic energy changed going from here to here, so say the kinetic energy in B minus the kinetic energy in A, all I have to do is to sum all of these little variations. And guess what? This is precisely integral, and therefore the work. So what we discovered is the very familiar idea that the difference in kinetic energy between any point, any 2 points, is given by the work performed by the system to go from A to B, for the mass of by the forces acting on the particle from A. Why I need to have this concept? Why do I care about this relationship? Well, because you see, it helps me solve so many problems. Let me give you an example that is very familiar to everyone. Suppose I want to understand what is the velocity of my particle that I drop, say, 1 meter high by the time it smashes the floor. Suppose I have my little mass at some height h. I leave it with velocity 0 at the beginning, and I want to know the velocity when it hits the ground after traveling through a distance h. Well, like I said at the beginning, all of this information is already encoded in Newton's law. So, you might say, solve Newton's equation with the initial velocity set to 0, initial position set to h, and then look at the position at which time the particle hits the ground and compute the time derivative of the trajectory at that time when the particle hits the ground. That's the Newton's law way of doing it. So basically one would say, I know the force is the gravity force, and then I can write that, I can write one coordinate z, so to say, and say the second derivative of this coordinate is equal to negative, it's a positive g because I'm setting the axis organized in this level. And then I can solve this and get the famous z of t equals z of time naught plus the velocity of time naught time t plus 1/2 g t minus time naught squared. Then I would, set this equal to h. It's not h bar, so h. Then calculate what t gives me that h. And once I know what t gives me that h, then I calculate the derivative of z in that time. You see how much work do I have to do in order to get the velocity when it hits the ground. Now, using the theorem we just derived together, I do this in one line. I say, okay, what is the work done by the gravitational force in going from A to B covering a distant h? Well, that's clearly times g times h. Because the force is always constant, and therefore it doesn't change from year to year. I can use even one single delta x, the force doesn't change. So let's say I use 1 and it's h. And on the other hand, I know the initial velocity is 0 and the final velocity is whatever it is the quantity that I want to calculate. So I simply have this super simple relationship. The mass goes away, and therefore velocity is basically the root of 2gh. Done. So this example clearly shows that that these concepts like work and kinetic energy are quite useful in classical mechanics whenever I have to get some information out of it. Not all of it, some, but I can get it very quickly. The price to pay is that I don't get the entire history of my particle. I get only information about the velocity, which is scalar, the modulus of the velocity in particular. But I can do that extremely effectively. The second concept I wanna work on and elaborate on is the concept of potential energy. So we discussed the concept of work from A to B, and we said that in general, this work depends on what path I need to go from A to B. Because suppose you're swimming, and while you swim, the force you have to exert, or the water actually has to exert on you, to be more precise, for you to go from A to B, has to overcome the viscosity of the water. And the viscosity of the water is always trying to oppose you. So that clearly If you take a longer route from going to A to B swimming, you have to win an opposing viscosity for a longer route. And then clearly this opposition will add up to a larger work. In other words, this is the reason why if you take a longer route, you consume more fuel on your car. As simple as that. But there are specific kind of forces which don't behave like that. Again, take the case of a particle rolling down, going from z equals h to z equals 0. And you can think about doing this, say, in different ways. For instance, you can do this by rolling down a plane or just dropping down this wall. Now, if this plane doesn't contain any friction, the force that a plane will exert on the particle, probably you remember, let's call it N, will be perpendicular to the plane, and the gravity will be going down. Now, since the particle will move in this direction, N times delta x will be always 0. So you will soon discover that the force is not the wall here. Oh, I'm sorry. I'm realizing as I speak that my screen was frozen, and therefore you might have not been able to follow what I was saying before. Okay, so let me just reshare the screen and go over this example again. I apologize for this inconvenience. Anytime I stop for some period of time, I have to do this. And if anytime I don't use my blackboard, whiteboard for a sufficiently long time, it has this problem. So what I was saying is that I have a particle rolling down a cliff, and the force that the cliff is exerting on the particle is perpendicular to the position, to the displacement of the particle. So the force that the cliff does on the particle doesn't make any work, and only the gravity makes work. Now, if you have a force that is constant, such as gravity in the proximity of the Earth, whenever you evaluate the work from A to B, you want to evaluate this integral. But remember, the force is constant. You can take it out because it's a constant now. It doesn't depend on your position. And therefore, you can discretize this in a unique step like we did before. And so this is simply f dot xb minus xa, right? And the striking thing is, regardless of the path you're doing from going from A to B. So whether you're falling down this direction or falling down this direction or falling down this direction. Whatever you do to fall. So in particular, for the particle that was covering a distance h in altitude, whether you would fall this way or this way, the work of the gravitational force would be the same, which implies that the final velocity will be orientated in different positions, but will be in modulus the same. So some forces are such that the work that they make is not depending on on the specific path that the force is actually doing. that the particle is actually going through. So these particular forces are called conservative forces, as you probably remember. There are many families of forces that are conservatives, and basically all fundamental forces are conservatives. And in particular, the central force are conservative, as I will elaborate later. Central force are force for which F is always perpendicular to the some radius from some center of the reference frame. So this is my position X. How do I write this? This is the vector from the system of origin and the position of the particle, and the force is directed along the same line. These are called central. For instance, the centrifugal force is a central force, the gravitational force is a central force. So also the central force have the properties of being conservative. Now, if a force is conservative, then you don't need to specify the path, and therefore what you can say is that the work to go from A to B depends only on one function that depends only the difference on one function, one evaluated of the final position and one evaluated in the initial position. So typically, you call this function potential energy. This is a definition of what is on the right-hand side. So the potential energy is a concept you only introduce for particles that are subject to conservative forces only. And it has the property that it allows you to evaluate the work done by the force going from A to B without having to know the path, just knowing the position in B and the position in A. This is the definition of potential energy, if you want. Now, this definition is very useful because if you now use the theorem we derived before, we know that the work is the difference of kinetic energy. And so if I bring things on the one on the side and the left-hand side, I get that the left-hand side is written as a sum of kinetic and potential energy. And the right-hand side is written as a sum of kinetic and potential energy. And what this is telling me is that no matter what I do, no matter what trajectories I follow, if I do have a conservative force, if I do have a conservative force, then the sum of kinetic and potential energy is going to be constant in every point of my trajectory. So I have my particle moving here. If I start with a particle point A, let me call this point B, let me call this point C, let me call this point D. And what I will going to have is that TA plus UA is going to be equal to TB plus UB, is going to be equal to TC plus UC, and so on and so forth. So the quantity E, sum of kinetic plus potential energy, is called mechanical energy. And this quantity is actually conserved. In the next lecture, and by conserved, we mean it doesn't change with, it doesn't change along the trajectory of my particle. In the next lecture, we'll introduce two more conservation laws that, like the conservation of energy, are very useful to gain information about the behavior of a system without having to solve Newton's law. And we later discovered during goal number 2 of this revisitation of classical mechanics that the importance and the relevance of these concepts is far more far more central than we anticipate at the level of classical mechanics. It turns out that these concepts are important and fundamental beyond classical mechanics, and they actually become the key of a physical theory in more general formulation. So their real importance is not so much that they can help you solve problems in classical mechanics, but they introduce ideas that remain there even when you abandon classical mechanics. And that's precisely what I meant in the metaphor of the ant being lifted from the ground and seeing things from a more general perspective, and discovering there were concepts such as nature versus, I don't know, street and asphalt and concrete that were more general than simply leaf and flower. Leaf and flowers were general concepts that, belong to nature, and nature was more general than leaf and flower. So in this metaphor, I'm trying to say the concept of energy and kinetic energy and potential energy are more general than classical mechanics and will be used also in the context of quantum mechanics. This is one of the reasons we introduced that at this level in our revisitation of classical mechanics. So next lecture, we're going to introduce 2 more concepts: the angular momentum L and the linear momentum P, discuss their conservation again, and then we will finally be equipped with the tool we need to address the question, what is a physical theory and what is really classical mechanics all about? But for that, we need to wait a couple of lectures. Okay, goodbye.